Hello students, I'm Dr. David Nagaratnam, a postdoctoral researcher in the Flow-Induced Noise and Cavitation Control Laboratory, Chungnam National University. Today I'll be presenting the Matlab implementation of an important numerical analysis technique frequently used by engineers and researchers called regression analysis. The objective of regression analysis is to fit the observed data points using a best possible model. In this presentation, we will learn about the Matlab implementation of simple linear regression, multiple linear regression, polynomial regression, and nonlinear regression. We will determine the coefficient of determination R squared and plot the fit between the data predictions and experimental observations. The script files used for the presentation are given in my personal web page given in the link shown here. The link is also provided in the description to the video below. A basic knowledge of Matlab coding is prerequisite in order to proceed with the coding. However, the script files shown here are simple to understand for beginners as well. In all the examples considered here, we'll be utilizing the general linear least squares method for the determination of model coefficients. At first, let us consider the simple linear regression of a single independent variable x. Clear CLC and close all commands. Clear the workspace window and the command window and closes all the currently displayed windows. The data points here are given in the variables x and y. Here x is the independent variable and y is the dependent variable. At first we are plotting the data points x and y, and then we are assigning the x label and y label. X label is x and the y label is y. And then we are forming a x matrix, which is essentially the stacking of ones in the column 1 and then the dependent variable x in the column 2. And then we have this function regress. Regress is the important command that is used in order to perform the regression in Matlab. Here the independent variable is y and the dependent variables are stacked in the matrix X. B is the variable which holds the model coefficients. Stats contains the coefficient of determination R squared. Now hold on command is then used in order to plot further plots on the same window in which the x and y variables are plotted. And then we stack the x variables such in an ascending order and store it in a variable x plot. Now, having determined the model coefficients, having them stored in the variable b, here as we are considering a simple linear regression, we have two model coefficients, namely a0 and a1, and they are stored in the variables b1 and b2. b1 plus the product of b2 and the x values gives us the y values. The model findings are then plotted on the same window in which the input data points are plotted. The model findings are plotted as x plot and y plot. And then the legends are assigned, the measured values and the model findings are assigned. Here the model finally, upon running the Matlab script, we find the model coefficients b1 and b2 to be equal to minus 10.9 and 0.43 respectively. And then the statistics, the stats variable has its first in its first element the r-squared value for the current data set using a simple linear regression model gives r-squared to be equal to 0.97. The Matlab script used for all of the models that we considered today are given in my personal webpage. I suggest you to kindly download those scripts and be benefited. Now, upon plotting the model findings against the measured values, we find such a fit which is linear in nature. The data points from our observations are given here. Let me encircle them for you to see clearly. With the observations being closer to the model predictions and r-squared value being close to 1, our simple linear regression model closely agrees with the observations. Now let us consider an example for multiple linear regression where we have a power law model. The power law model is shown here. We have a constant coefficient and then we have two independent variables, namely x1 and x2. x1 is raised to the power beta and x2 is raised to the power gamma. The x1 value and x2 values are and the independent variable y are tabulated here in this table. Now, in order to proceed further, we linearize the nonlinear problem. In order to linearize, we take logarithm on both sides. Logarithm of y is the logarithm of alpha plus beta times logarithm of x1 plus gamma times logarithm of x2. Now we assign logarithm of y as capital Y and then logarithm of alpha to be a0, beta to be equal to a1 and gamma to be equal to a2, and then logarithm of x1 is capital X1 and logarithm of x2 is capital X2. Now we have the nonlinear problem written in linear form as shown here. Y is a0 plus a1 times x1 plus a2 times x2. We have such a linear model. Now let us proceed towards Matlab implementation of it. First, we are using clear, CLC and close all commands. Clear clears the workspace window, CLC clears the command window, and then close all closes all the existing open windows currently in the Matlab. Then we assign x1 to be equal to the first independent variable, x2 to be equal to the second independent variable, and y is the independent variable. Logarithm of y is capital Y, logarithm of small x1 is capital X1, logarithm of small x2 is capital X2. And then we form the matrix X, which is essentially the stack, which has the stackings of the independent variable. Here we are stacking as the first column. In the first column, the column of ones, whose number of rows is equal to the length of x1. And then as in the second column we are stacking capital X1 and the third column we are stacking capital X2. Thus we have formed a matrix X, which is essentially formed by stacking the independent variables. And then as an input to the regress function, we input the independent variable and the matrix of dependent variables in the variable b. We have the model coefficient stored. Remember, we are taking logarithm on both sides, and hence we have to take exponent of b1 in order to know the constant coefficient of our model. The constant coefficient of our model is alpha. And then we have b2 to be equal to beta and b3 to be equal to gamma. And hence finally our model is given as shown here. It is alpha times x1 times beta times x2, alpha times x1 to the power gamma times x2 to the power gamma. B1, B2, B3 are the model coefficients, and statistics first element is the R squared value. It is equal to 0.99. Now let us consider the same example solved without a constant coefficient. That is, we don't have alpha over there, alpha over here. Instead we have x1 raised to the power alpha and x2 raised to the power beta. Now let us proceed towards solving such a nonlinear model without a constant coefficient. Capital Y is formed by taking a logarithm of y, and capital X1 is logarithm of x2. Capital X2 is logarithm of small x2. Essentially what we are doing is taking logarithm on both sides in order to linearize the nonlinear problem. And then we form a matrix of independent variable formed by stacking capital X1 and capital X2. And then we use a regress function where the independent variable is y and the dependent variable is a matrix of x, matrix x. Here B is the model coefficient, as the B's elements are the model coefficients. Alpha is stored in B1 and beta is stored in B2. And the stats variable's first element is going to be the R squared value. Now x1 raised to the power alpha times x2 raised to the power beta gives us the model findings. B1 and B2 for this particular data set is found to be equal to 1.73 and minus 0.03, minus 0.0365. And statistics or the R squared value is equal to 0.49. We see that by looking at the R squared value, we find that the model with the constant coefficient was returning as a larger value of R squared. Now let us consider the polynomial regression. Now we'll first consider the polynomial regression of the order 2. The independent variable is x and the dependent variable is y. At first we plot the independent variable against we plot the dependent variable against the independent variable using the plot command, and then we are assigning the labels to the axis, x label and y label, and then we are stacking the independent variables. We are forming a matrix X. The first column is the column of ones, the second column is the column of X, and the third column is the column of X squared. To the regress function, we input the independent variable Y and the dependent matrix X, and then in B we save the model coefficients are saved in B, and in stats R squared value is saved. The stats first element is R squared, and then in the open window we continue to plot the model findings, and hence we use the hold on command, and then we in between the maximum and minimum value of x we are assigning 1000 data points. And then we in the model predictions using yplot, we save it in yplot. Here the model coefficients are b1, b2 and b3, and we have x b2 multiplied with x and b3 multiplied with x squared. Now upon plotting the model findings, plotting x plot and y plot and assigning the legend values, we find b1 to be equal to 34.2, b2 to be equal to 0.1 and b3 to be equal to 0.007, and stats being equal to 0.99. Upon plotting, we find the model findings to be closely agreeing with that of the measured values as shown by these circle points. Now let us do the same polynomial regression using an inbuilt function exclusively provided by Matlab for performing the polynomial regression or the polynomial fit called a Polyfit and Polyval functions, which are unique features of Matlab. Now we have the dependent variable given by y and the independent variable is x. N is the order of the polynomial. At first we are plotting x and y, and then we assign the x label and y label. Polyfit function essentially finds the coefficients of the polynomial which we are considering polynomial of the order n. Here n is equal to 2. The model coefficients, namely a0, a1 and a2, will be stored in B, and then we are using hold on function in order to continue plotting on the same open figure window. Between the minimum and the maximum values of x, we are assigning 1000 data points, and we are evaluating we are finding the model findings. We are evaluating the polynomial whose coefficients are in B, with the x values being x plot. The final values are stored in y plot, and then we plot x against y over here, and then we assign the legend. B1 we find to be equal to 0.007, B2 is equal to 0.101, B3 is equal to 34.2. Now, unlike the previous regress command which we used, in which B1 was equal to 34, B2 was equal to 0.1 and B3 was equal to 0.007, the inherent building of Polyfit and Polyval is such that B1 is the largest exponents coefficient, and in the successive order, B3 is the constant coefficient. Upon plotting the measured values against the model findings, we find a close agreement between the model findings and the measured values. Now let us consider the nonlinear regression in Matlab. There is an inbuilt function provided in Matlab called nlinfit. We will learn about that function shortly. At first, let us consider the model that we are interested in. That is, there is a constant coefficient a0 and a1. This is the nonlinear model which we are considering. It is essentially an exponential model. a0 times 1 minus e to the power a1 into x. Here, as an input into the model, we input the independent variable x and the initial guess value and the value of a. A contains the model coefficients a0 and a1. The model is evaluated here and saved in f. F will be returned upon inputting x and a into this particular function. F will be returned. The model will be evaluated and returned. Now this is one particular function called prob. Prob.m will be the called function. The main function begins from the line 1 shown here. At first we are clearing the workspace window and then clearing the command line window, and then closing all the existing windows in Matlab. X is the independent variable, y is the dependent variable, and then we are giving an initial guess value for a. Here a is the matrix of matrix or the vector of the model coefficients, initial guess value for the model coefficients. Here A0 is assigned an initial guess value of 1 and A1 is also assigned an initial guess value of 1. Now this line is essentially assigning a function handle for the prob function. Here the prob function evaluates the model upon inputting the model coefficient and the independent variable. Here fun is the function handle for our prob function. At first we plot x and y, and then we define the x label and y label. Now nlinfit is the function that is unique to Matlab, which iteratively evaluates the model coefficients upon inputting the independent variable x and the dependent variable y and the function or the model which we want to evaluate. Here fun is the function handle, a is the initial guess value, nlinfit essentially iteratively evaluates the general linear least squares method for these inputs x, y and the nonlinear function and a. A is the initial guess value. Now beta has the final model coefficients, and then on the open figure window x plot and y plot we want to plot the model findings. Between the minimum x value and the maximum x value 1000 points are assigned, and then we evaluate the function for the iteratively finalized model coefficients saved in beta as an input to the function, and then we also input the independent variable and finally obtain y plot. Now finally we plot the model findings in using this particular plot command. X label and y label are finally assigned, and then we assign the legends. Now upon plotting we find a good agreement between the model findings and the data observations given unto us, as shown by these encircle points lying close to the curved line. Beta 1 and beta 2 are equal to 0.79 and 1.67. Now there are inherent assumptions in using these linear least squares model. At first, each x value has a fixed value and it is not random and is to be known without error. And then y values are independent random variables and all must have the same variance. And y values for given x values must be normally distributed. These are some of the inherent assumptions which are involved. Some more theory on this topic can be found in Draper and Smith and Chapra and Kennel. I thank you all for your attention once again. The Matlab scripts which are used in this particular presentation are found in my website. I request you to please download those script files and be benefited. God bless. Please share this video with your friends who will also be finding it useful. Thank you for your attention once again.